The arrangement of a common neutral for all fluorescent fixtures is generally acceptable under the National Electrical Code, often abbreviated as NEC, and is commonly used in commercial lighting applications. Although the NEC does not explicitly address common neutrals on branch circuits, it allows them on feeders in Article 215.4.1. A feeder is a circuit that supplies a branch circuit or a lighting system. Therefore, by extension, common neutrals can be used on branch circuits that supply lighting fixtures. If the manufacturer of the fixtures in question, has confirmed that it has no problem with a common neutral, this indicates that the fixtures are designed and tested to operate safely with a common neutral. Using a common neutral has the advantage of balancing the electrical load among the three phases. This helps ensure that the voltage drop on each phase is approximately the same. However, there might be objections to a common neutral. Firstly, potential voltage drop. If the load on one phase is significantly higher than the others, it could cause a voltage drop on that phase. This could result in reduced light output from the fixtures on that phase. Secondly, increased neutral current. Using a common neutral can increase the current flowing through the neutral conductor. If the neutral wire is not properly sized, it could overheat and pose a safety hazard. These concerns can be addressed by taking the following steps. Firstly, proper fixture arrangement. Arrange the fixtures and the phases to ensure that the load is balanced as much as possible. Secondly, adequately sized neutral. Calculate the total current flowing through the neutral wire and select a wire size that is rated to handle the load safely. Based on the information provided, using a common neutral for the fluorescent fixtures is acceptable under the NEC and should not pose any safety hazards provided that the concerns mentioned above are addressed. It is recommended that you consult with a qualified electrician to confirm the feasibility of the proposed arrangement and to ensure that all applicable codes and standards are met. When considering a common neutral arrangement, the National Electrical Code, NEC, provides guidance, although it doesn't explicitly detail branch circuit scenarios. Article 215.4.1 addresses feeders, which are circuits supplying branch circuits or lighting systems. The permissibility on feeders suggests that similar principles can be applied to branch circuits serving lighting fixtures. The fixture manufacturer's approval is crucial. Their confirmation indicates that the fixtures are designed and tested for safe operation with a common neutral. This is important as it validates the compatibility of the fixtures with this wiring configuration. Electrical load balancing is another key advantage. A common neutral helps distribute the electrical load evenly across the three phases. This balance ensures that the voltage drop on each phase remains consistent, contributing to stable and efficient operation. Concerns often arise regarding potential voltage drop and increased neutral current. To mitigate these concerns, several measures can be taken. Firstly, ensure proper fixture arrangement. Strategically distribute the fixtures across the phases to balance the load as effectively as possible. Secondly, use an adequately sized neutral conductor. Calculate the anticipated total current flowing through the neutral wire. Then select a wire size that is rated to handle the load safely, preventing overheating and potential hazards. To elaborate on load balancing, consider a scenario where the lighting system consists of numerous fluorescent fixtures, each with multiple ballasts. Distribute the fixtures across the three phases, Phase A, Phase B, and Phase C, in a way that equalizes the current draw on each phase. If one phase has a significantly higher load than the others, it can lead to a voltage drop on that phase. This voltage drop can dim the lights connected to that phase and potentially damage the ballasts over time. Therefore, striving for an even distribution of fixtures is crucial. Calculating the neutral current requires understanding the nature of three-phase systems. In a balanced three-phase system with purely linear loads, the neutral current is ideally zero. However, in real-world scenarios, especially with lighting systems, imbalances are common. These imbalances can result from variations in ballast performance, slight differences in voltage between phases, and the presence of nonlinear loads such as electronic ballasts. To calculate the maximum neutral current, you can use the following approach. Firstly, measure the current on each of the three phases, Phase A, Phase B, and phase C under the maximum expected load conditions. Secondly, calculate the imbalance by subtracting the smallest phase current from the largest phase current. This difference represents the potential neutral current. Thirdly, select a neutral conductor size that is rated to carry at least this calculated current, plus a safety margin. The NEC provides tables and guidelines for determining the appropriate wire size based on the ampacity and insulation type. Using an undersized neutral conductor can lead to several problems. Firstly, overheating. An overloaded neutral conductor will generate excessive heat, which can damage the insulation and potentially cause a fire. Secondly, voltage drop. The increased resistance of an undersized conductor will contribute to a voltage drop, further exacerbating the problems caused by imbalanced loading. Thirdly, nuisance tripping. In some cases, the excessive neutral current can trigger ground fault circuit interrupters, abbreviated as GFCIs, or arc fault circuit interrupters, abbreviated as FCIs, leading to unexpected power outages. Consulting with a qualified electrician is highly recommended. An experienced electrician can assess the specific characteristics of the lighting system, perform accurate load calculations, and ensure compliance with all applicable codes and standards. They can also identify any potential issues or concerns that may not be immediately apparent. Furthermore, local codes and regulations may have additional requirements or restrictions regarding the use of common neutrals. An electrician can provide guidance on these local requirements and ensure that the installation is fully compliant. In addition to load balancing and conductor sizing, other factors can influence the performance and safety of a common neutral lighting system. These include, firstly, the quality of the ballasts. High-quality ballasts are more likely to operate consistently and reliably, contributing to better load balancing and reduced harmonic distortion. Secondly, the type of lamps. Different types of fluorescent lamps have different electrical characteristics, which can affect the overall load profile of the lighting system. Thirdly, the presence of other loads on the same circuit. Other electrical loads connected to the same branch circuit can contribute to imbalances and increase the neutral current. Therefore, it is important to consider all of these factors when designing and installing a common neutral lighting system. Common neutrals are more prevalent in commercial settings due to the efficiency and cost savings they offer in three-phase systems. In residential settings, single-phase power is more common, reducing the necessity for common neutral configurations. The decision to use a common neutral should be based on a thorough assessment of the load characteristics, code requirements, and safety considerations. Ignoring these factors can lead to performance issues, safety hazards, and code violations. It is important to note that the NEC is updated regularly to reflect changes in technology and best practices. Therefore, it is crucial to consult the latest edition of the NEC and any applicable local amendments before designing or installing any electrical system. Furthermore, continuing education and training are essential for electricians and other electrical professionals to stay up to date on the latest codes, standards, and technologies. This ongoing learning ensures that electrical installations are performed safely and in compliance with all applicable requirements. Understanding the application of NEC Article 310.15 concerning ampacity of conductors is essential for proper neutral sizing. This article provides detailed guidelines and tables for determining the allowable ampacity of conductors based on factors such as insulation type, ambient temperature, and the number of conductors in a raceway or cable. Correctly applying these guidelines ensures that the selected neutral conductor has sufficient capacity to carry the anticipated current without overheating. In addition to the NEC, other standards and guidelines may be relevant to the design and installation of common neutral lighting systems. These may include standards from organizations such as the Institute of Electrical and Electronics Engineers, abbreviated as IEE, the National Electrical Manufacturers Association, abbreviated as NEMR, and Underwriters Laboratories, abbreviated as UL. These standards provide valuable information on topics such as power quality, harmonic distortion, and equipment safety. Consulting these standards can help ensure that the lighting system is designed and installed to meet the highest levels of performance and safety. When evaluating the feasibility of a common neutral arrangement, consider the potential for harmonic currents. Harmonic currents are non-sinusoidal currents that can be generated by nonlinear loads such as electronic ballasts. These currents can add to the neutral current and potentially overload the neutral conductor. If harmonic currents are a concern, it may be necessary to use a larger neutral conductor or to install harmonic filters to reduce the level of harmonic distortion. Proper grounding is also essential for the safe and reliable operation of a common neutral lighting system. The grounding system provides a low impedance path for fault currents, helping to protect equipment and personnel from electrical shock. Ensure that the grounding system is installed in accordance with the NEC and that all connections are tight and corrosion-free. Regular inspection and maintenance of the lighting system are important for ensuring its continued safe and reliable operation. This includes checking for loose connections, damaged wiring, and other signs of wear and tear. Promptly address any issues that are identified to prevent potential problems. In conclusion, using a common neutral for fluorescent lighting fixtures can be an acceptable practice under the NEC, provided that certain conditions are met. These conditions include ensuring proper load balancing, using an adequately sized neutral conductor, and addressing any potential concerns regarding voltage drop, harmonic currents, and grounding. Consulting with a qualified electrician is highly recommended to ensure compliance with all applicable codes and standards and to ensure the safe and reliable operation of the lighting system. The NEC permits common neutrals for feeders, as stated in Article 215.4(1), which indirectly supports the use of common neutrals for branch circuits in specific conditions, particularly when supplying lighting fixtures. This acceptance hinges on careful consideration of load balancing, conductor sizing, and adherence to safety standards. Factory approval from manufacturers like Lithonia is crucial. Their confirmation ensures the fixtures are designed to operate safely with a common neutral configuration. This endorsement indicates that the fixtures have undergone testing to validate their compatibility with this wiring arrangement. Load balancing is a significant advantage of using a common neutral. By distributing the electrical load evenly across the three phases, the voltage drop on each phase remains consistent, contributing to stable and efficient operation of the lighting system. This balance is essential for maintaining optimal performance and preventing potential damage to the fixtures. However, potential drawbacks must be addressed. Voltage drop, especially when one phase carries a significantly higher load, can lead to reduced light output and potential damage to ballasts. Increased neutral current, if the neutral wire is not properly sized, can cause overheating and pose a safety hazard. To mitigate these issues, strategic measures are necessary. Fixture arrangement should be optimized to ensure that the load is balanced across the phases as much as possible. Adequate sizing of the neutral conductor is paramount. Calculating the total current flowing through the neutral wire and selecting a wire size that can handle the load safely are essential steps. Consulting with a qualified electrician is highly recommended. A licensed electrician can assess the specific characteristics of the lighting system, perform accurate load calculations, and ensure compliance with all applicable codes and standards. They can also identify potential issues and provide tailored solutions. Local codes and regulations may impose additional requirements or restrictions on the use of common neutrals. An electrician can ensure that the installation meets all local requirements and complies with the latest updates to the NEC. Proper planning, installation, and maintenance are essential for the safe and reliable operation of a common neutral lighting system. This includes regular inspections, tight connections, and addressing any signs of wear and tear. Additionally, understanding NEC Article 310.15, which covers conductor ampacity, is crucial for proper neutral sizing. This article provides detailed guidelines and tables for determining the allowable ampacity of conductors based on various factors. Other relevant standards from organizations like IEE, NEMA, and UL can provide valuable information on power quality, harmonic distortion, and equipment safety. Consulting these standards can help ensure that the lighting system is designed and installed to meet the highest levels of performance and safety. Consider the potential for harmonic currents generated by nonlinear loads such as electronic ballasts. These currents can add to the neutral current and potentially overload the neutral conductor. Proper grounding is crucial for protecting equipment and personnel from electrical shock. The grounding system should be installed in accordance with the NEC, and all connections should be tight and corrosion-free. Regular inspection and maintenance can help ensure the lighting system's continued safe and reliable operation.